Here's the topic du jour is linear inequalities in two variables. Look at the solutions of linear inequalities in two variables. So what we want to be able to do by the end of the day, you're going to understand how to graph linear inequalities in two variables, what it means to be a solution of a linear inequality in two variables. And then on the assignment, I'm going to have you even do that backwards, where I, given a graph, can you write what the function looks like, or what the inequality looks like. You write the linear inequality in two variables. So let's take a look at this stuff. Before we jump into the new stuff, though, I want to here's how we can put this in context that'll make it more understandable. Let's remind ourselves real quick what it means to be a solution of an equation. So we got the simple equation here, 3x plus 2y equals 2. What's it mean to be a solution of that equation? What's that going to look like, first of all? What do you think?
Well, like solving off the top of my head, it would be y equals negative 1/2 x plus 1.
Okay, so one thing we could do, if we want to, we could rewrite the form of this, and that might be useful. If we were to isolate the y, solve for y, what are the two steps in order we would go through to get the y by itself? Okay, I'm going to subtract 3x from both sides, right? If I do that, if I subtract 3x, over here I just get a 2y. On this side I get a negative 3x plus 2 divided by 2. If I divide both sides by 2, okay, now, and this is kind of important review stuff. If I'm dividing on the left side, I just get my y, which was the goal. On the right side, if I divide the whole thing, both terms, by 2, I'm really dividing twice, aren't I? What's the first? If I want to split this up, right there's I've got this written in terms of a common denominator, but maybe I don't want that. What if I want to write it as two separate terms? Well, I can just deal with them separately. If I ignore the 2 and just divide the first term by 2, what do I get? Okay, negative 3/2 x. And what about the second term? Plus 1, 2 divided by 2? Okay, that's fine. But we still haven't solved it. All we've done is we've rewritten the equation in a different form. Maybe this is a better form for us. That looks pretty familiar. What form is that in? Y equals mx plus b. So we're talking about a line, aren't we? And this is just what we call standard form for a line. We've looked at that a little bit in the past, and we'll see that throughout the year. But once again, we still haven't answered the question, what's a solution? But even before we get there, what's it even going to look like?
You have to graph it.
Yeah, I could graph it. I don't have to graph it, though, to talk about a solution. And we will graph it. What is a solution going to be? Let's start with a simple one, maybe. What if I just gave you something like this? 2x minus 1 equals 5. What's a solution of that equation? Say it again. X equals 3, and you get that by adding 1 and dividing by 2. So you're right, that's the solution. X equals 3 is the solution, because what's it do to the original equation?
Simplifies it.
Well, okay, so we gotta make sure we get the words right. I know what you're saying, but simplify, in a sense, yes. To simplify is to write something in a simpler form. But the word we use in math is, it satisfies the original equation, that value of x, meaning it makes it true, right? It makes the equation true, right? Okay, so it satisfies the original equation, it worked. So my equation just looked like a value for x in this simpler green equation. Now, this is a little more complicated. What's the solution going to look like to the blue equation? What do you think? Suggestions? Okay, this isn't the solution. This is just a restatement. I don't know if we call it simplifying or not. We just rewrote the equation in a different form. We isolated y, but I still have variables in there, so it's not solved. Okay, yeah. Now, what if I were to plug in a value for x and a value for y? And I could just pick some arbitrary values. If I plug in x equals 2 and y equals 5, for example. If x equals 2 and y equals 5, does that work? If I plug in 2 for x, I get negative 3 halves times 2 is negative 3 plus 1, and I get 5 on. That's not true, is it?
No.
That's not a solution, but it might have been if we just picked different numbers, right? Would you agree that the solution in this case, the difference between the blue and the green equations is that this had one variable and that had two? Dylan, you have an idea?
X equals 0, y equals 1.
Okay, that would work. That's a solution, isn't it? If I try the solution x equals 0, well, if I plug 0 into this equation, anything times 0 is what? 0. So I get the answer y equals 1. Right? So when x equals 0, y equals 1, and an easier way to write that would be as an ordered pair, right? Because I know I'm going to need an x value and a y value here. I need values of the two different variables that would satisfy the original equation. That works, doesn't it? Checks out. Is that the only solution we could have chosen? No. In fact, we could make a t-table if we wanted to, and I could make a whole list of values, right? We chose x equals 0 and got back y equals 1, but I could choose any number of values of x that I want to. For every value of x that I choose, I'm going to plug that into the original equation and just solve for y, right? And I'm going to get back for each different value of x, I'm going to get back a different value of y in order to pair. Now, if we think about this in terms of a graph, it's important what happens here. If I graph this point 0, 1, I know that's a solution, right? If I graph the point 0, 1, I'm right here, that's a solution. What is the graph of all the solutions going to look like? Each one of those solutions, we said, was an x and a y value, right? So for example, if I plugged in x equals 2 in my t-table, that's a pretty easy one, right? If I plug in x equals 2, what do I get back for y? 2 times negative 3 halves is what? Negative 3, right? 2 over 1 times negative 3 over 2. The 2's would cancel. Negative 3 plus 1 is? So that's another one, right? If I plot that one over 2 and down 2, there's another solution. What if I plotted all of them? What shape would it make? It's going to make a U. It's going to make a line, right? And I know it's going to make a line because that's the equation of a line. Right? I didn't even really have to plot that second point. I could have just used a slope triangle. I know that this tells me that the y-intercept is 1, doesn't it? Mx plus b. So that's telling me 1. And this negative 3 halves, if I just make a slope triangle, isn't that saying I'm going to rise by negative 3 and run by positive 2? Right? And so if I were to string all those ordered pairs, all those points together, their graph would just look like that line. So that's the graph of the solution set. Yes, ma'am?
Hey, teacher, have no arrows.
Those are pretty bad arrows, aren't they? Need to go back to teacher school and learn how to make arrows. There we go. Okay. So we get all those points taken together make the line. An individual solution would just be an x and y value that makes the original equation true. Okay? Okay, so moving on. Then what's going to be the difference between a linear equation and a linear inequality? Okay, well let's take the same numbers. But instead of 3x plus 2y equals 2, let's do 3x plus 2y is greater than or equal to 2. Okay, I could, just like before, if I want to test to see if these x and y values, these ordered pairs or solutions, what could I do? In order for the point 0, 0 to be a solution, what would have to be true? What makes it a solution of that inequality?
0, 2, right? 2.
Okay, right, because if I plug in the values of x and y, it's either going to make this true or not. If it makes it true, it's a solution. If I plug in 0, 0, look what I get. I get 3 times 0 plus 2 times 0, right? If I plug in 0 for x and y, that's just 0. 0 is greater than or equal to 2. Is that true or false?
False.
That's false. So is it a solution?
No.
No, it's not. It's not part of the solution. When we end up graphing the solution set of this linear inequality, that is not going to be part of the solution set that's graphed. What about 2, negative 1? Well, that's going to work. If I plug that one in, 3 times 2 is 6, plus 2 times negative 1 gives me 4. 4 is greater than or equal to 2, isn't it?
Yes.
So that one is a solution. And then this guy here, same kind of thing. That would work also. 3 times 0 plus 2 times 2 is 4. 4 is greater than or equal to 2, so that also works. So the second two are solutions, the first one was not. So it's easy for us to test solutions, but now let's take an additional step and say, how do we graph a set of all the solutions? Okay, the good news is, it's very similar to what we just did. In fact, probably half or more of what we do is just graphing the line associated with this inequality. All the graphs of linear inequalities, two variables, all look essentially the same. There's going to be two parts. There's going to be a boundary line, which is the same as the line we just graphed. And then there's going to be a shaded region, a shaded half plane. If I draw a line through the xy plane, the line extends forever. It cuts that xy plane into two infinite half planes, one on one side and one on the other. One of those two half planes will always get shaded. Okay? The question is just which one. So our strategy is going to be simple. We're going to graph the boundary line, and then we're going to see which, by testing a point on one side or the other of the boundary line, we can determine which side gets shaded. And we just shade that side, and that's it. That's all there is to it. So there's not very much extra to do. Here's kind of just a summary of what we're going to do. They say 3 steps, I say 2. Graph the boundary line. Now there's one important thing you got to pay attention to here. If the inequality includes an equal sign, then that means that our line is going to be solid. If the inequality does not include an equal sign, it's going to be dashed. How come, do you suppose?
So you can't mix it up?
Okay, so we can't mix it up, that's true. But there's something else that's communicating to us. If the inequality includes an equal sign, doesn't that mean that the equation is also part of the solution? Right, so the line is going to be part of the solution set, the region that gets graphed. Agreed? If I'm not including an equal sign, the line is not. The line is just the boundary between the shaded region and the region that's not shaded. So we make it dashed to indicate that it's not part of the graphed solution. It's just the boundary. Let me get all the phones and stuff away, please. Put them in your pockets. I just want those out of sight, out of mind. Okay, and then the second one, we'll just pick a point and test it. So let's look at an example. 3x plus 2y is greater than or equal to 2. Okay, we could put it into slope-intercept form if we want to. We already did that. Is it going to be solid or dashed? The boundary line. Solid. Solid, right? Because it includes an equal sign in the inequality. So the first step is, let's graph the boundary line. We already did that. That's what we did at the beginning of class. That was the line that we graphed, right? We just took the line y equals negative 3/2 x plus 1. Solid because it includes the equal sign. We had a y-intercept at 1. Remember this? We had y-intercept at 1, and then we went down 3 and over 2 to get to the second point, connected and extended. That's the boundary. Now, which side gets shaded? Well, one or the other. Let's test an easy point to see. What's the easiest value to plug in for x or y? If we're trying to test to see if a point is a solution.
0, 1.
It'd be, well, 0 would be the easiest, wouldn't it? Right, zeros are easy because when I multiply by 0, you don't have to think very hard about that. What's the answer always? 0, right? So we're always going to test, anything times 0 is 0. So we'll always test the point 0, 0 if we can. Meaning if it's not on the line itself, not on the boundary line. Okay, in this case it's not, so we'll test it. If the boundary line goes through the origin, we can't use that point to test because it's not, it's got to be on one side or the other. We pick another easy point. It wouldn't be quite as easy, but still we can pick an easy one. 0, 0 works in this case though as a test point. Now if 0, 0 works in the inequality, what does that tell you about the points on the bottom left of that boundary line.
It's shaded.
Yeah, they're gonna be the solutions, aren't they? Because 0 works, so 0's gotta be in the half plane that includes all the solutions. So I would shade the side with the test point if it works. What if it doesn't work? Then it's not a solution, so it can't get shaded. Which side has to get shaded then? The other one, right? Shade away. If the test point fails, you shade away from it. So let's try it. If I try the point 0, 0, I can either plug it into the original inequality or I can plug it into the slope-intercept form. It doesn't matter. Either way, I'm going to get a statement that is true or false. False. If I plug 0, 0 in up here, I get 0 is greater than or equal to 1, which is also false. Both cases, it's false. Yes, ma'am? Yeah, go ahead. So it didn't work, and so that means that I have to shade away from that point. I shade the other side. That's it. Right? That's all we have to do. Let's look at one more of these. Okay, y is less than 6. Well, I guess I put the solution up here. Let's just see why this is the case. What's that boundary line look like? If we're going to break this into two parts, the boundary line is just going to be the line y equals 6, dashed or solid. Dashed because there's no equal sign there, right? So the boundary line's not included. And just quick review, this is actually a really easy line to graph, but there's no x in it, so sometimes people find it confusing. What's that line going to look like? If I have y equals a constant, y equals a number, it's always got to be a horizontal line. And sometimes people mix it up. Is it horizontal or vertical? Well, it's horizontal, and here's an easy way to remember that. If I compare that to mx plus b, if the x doesn't even show up, what's that mean that the slope must have been?
0.
Had to be 0. So is a 0 slope, does that represent a horizontal line or a vertical line? Well, it's got to be horizontal, because a vertical one, that's no slope, that's undefined, right? It's got to be the horizontal one, which we can also see from a slope triangle. If I just take 2 points and I connect them with a slope triangle, and the slope is 0, well, slope equals rise over run. If the slope is 0, what's that mean that the top of the fraction has to be?
0.
0, because 0 divided by any number is 0. Now, I can't divide by 0 itself, but 0 divided by another number is equal to 0. So if I'm rising by 0, I'm not going up or down at all. I'm only going to run, move horizontally. So the 2 points are always going to be lined up horizontally then, aren't they? For a 0 slope, right? So I know that I get this dashed horizontal line at y equals 6. Okay? It's got a y-intercept of 6 and 0 slope. Which side gets shaded? Well, I could test the point 0, 0. So 0 by 6, right? I could test the point 0, 0 in my original equation, but there's no x. Does that matter? No, it doesn't. It just makes it easier. I'm just going to plug a 0 in for y, and that's all I have to do, because there is no x. It gives me the statement 0 is less than 6. Is that true?
Yes.
Yeah, so I shade that region with the test point. There's another little shortcut I'll tell you too. You don't have to remember this, but I think it's useful. So 2 is we shade that region. If you ever have an inequality with x's and y's that's in the form mx plus b, all you have to do is just look at the direction of the inequality sign, and that automatically tells you to shade above or below the line. If it's in the form mx plus b, so think about what this is saying. If y is, for example, greater than some line mx plus b, y is a vertical quantity, right? It's the vertical coordinate. So if y is going to be bigger than the line, doesn't that mean that we're talking about the region that is vertically bigger than it, meaning above it, right? If I have y is less than some line, mx plus b, then I'm shading below. So I want the y values that are less than, meaning lower than the line. Okay, but I can always just test a point too. Question?
What about the equal? Like if it's equal or something?
Then it would be just a plain old equation. We would just graph the line only. Okay? Make sense?
Yes.
Okay? I could do another example, but almost think I've got the assignment up, why don't you just go do one down in the lab and make sure you got this?